Welcome back. Let's take another example from damped Harmonic oscillator, and here we are going to take example of the spring mass system. So I've got a coupled spring mass system like this. We discussed about this in one of the previous videos. We've got a spring attached to two ends of a wall, and the other end of the spring is attached to a mass which is initially in the center. We displace it out to a corner and release it, and it goes back and forth and oscillates. And last time we did not consider friction, and as a consequence it was a simple harmonic oscillator oscillating with a uniform frequency and uniform amplitude. But this time we will consider that there is some friction in this problem, and as a consequence, as the mass oscillates back and forth, it's eventually going to slow down and come to a stop. So we are going to analyze this problem. Let's look at this problem statement. First we are going to do is find the equation of motion, assuming that the coefficient of friction is mu and spring constant is k. Natural length of the spring is a0. So let's go ahead and work this out, and after that we're going to look at the time scales in the problem. The two time scales in the problem, there's a time scale associated with oscillation and there's a time scale associated with the damping. And then finally we are going to assume that the friction is small and calculate what is the rate at which energy in the oscillator is changing and the rate at which amplitude is changing. So let's go ahead and get started with that. So let's first analyze what is the equation of motion for the system. We've got a mass which is being displaced, and we worked out last time that mx double dot, let's assume there is no friction, and let's assume that from its mean position the mass has been displaced to the right hand side. As a consequence, there's a stretch in this spring, and the force because of this spring is to the left. So we have got mx double dot equal to k times the stretch in the spring, that is a plus z minus a naught. That's the elongation of the spring. The force in this is the negative direction, so that gives me that. And because of the spring on this side, again the force is going to be in the left direction because the spring will be contracted. We are assuming this extreme case. So again I've got minus sign for the force, and then I've got k, and I've got the contraction is a naught minus a plus z. Contraction is a minus z. The length of the spring is a minus z, and a naught is the natural length, so a naught minus a minus z, which is a naught minus a plus z, is the elongation in the string. Multiplied with k gives me the force, and if I add these two terms, I see that a cancels out. I see that a naught cancels out, and I get minus kz from here and minus kz from here. So my net force is minus 2 kz. That's what we did last time. Now when we add friction, then the friction force always acts opposite to the velocity. If the mass is moving this way, then the friction force is acting in that direction, and if the mass is moving this way, then the friction force is acting in that direction. So friction force is always opposite to the mass, and that only requires adding a correction. So my equation becomes mx double dot equals minus 2 kx, which is the spring force, and I have to add the friction force, which is always opposite the direction of velocity. To write that, I say, and the friction force magnitude is mu n, so ff is mu n, which is mu mg. So it's minus mu mg. It's always opposite to the direction of force, so it's a signum function of x dot. What is signum function of x dot? Well, it's simply plus 1 for x dot greater than 0 and minus 1 for x dot less than 0 and 0 for x dot equal to 0. So that's the signum function. If the block is moving, the friction force will always will be acting opposite to that, and that is taken care by the signum function. And as you notice that the signum function is not a continuous function. It's if you make a plot of this, it's going to be plus 1 on this side, minus 1 on this side, and 0 over here. So this is not a smooth force, this is not a smooth function. Therefore, we will find that it's hard to solve this equation analytically, and therefore we may have to solve this equation numerically. And that's why we talked about some of the numerical methods such as NDSolve, which we'll use in this example. But for now, that's our equation of motion. This is our equation of motion that we are interested in. Now let's talk about what are the time scales involved in this problem. The time scales involved in this problem are again of two varieties. Let's first ask what are the constants involved in the problem, or what are the scales involved in the problem. The scales involved in this problem are mass, the spring constant K, of course the gravitational constant G, and rather, since it's only mu G that comes together, we can call it mu G, which is the deceleration due to friction. So the scale is mu G, and those are the natural scales that are visible in the equation, but there is also the scale associated with the amount of displacement that we make to the spring, so that you can consider as A naught or A. Either of the two will work, because we are just doing a dimensional analysis. We are talking about dimensional analysis. We are only interested in the scales of the problem. The actual displacement that we start out for the system in the beginning is going to be of the order of A naught or of the order of A. So these are the physical scales present in the problem. Now coming to time scales. Time scales in this problem, one thing that is obvious is if you look at this equation. If you look at this equation, the oscillation frequency omega was given by square root 2k by m, which gives me the oscillation time scale. So oscillation time scale is 2 pi by omega, so it is 2 pi by m by 2k. That's the oscillation time scale in this problem. And there is damping time scale, T-damping. For damping time scale, we need to look at the damping term. The damping term has got mu mg, which is the force, divided by m, the mass, gives me the acceleration, which is simply mu g. So I've got acceleration mu g, and if I want to extract a time out of this, I should divide it by a length scale and invert it. So if the only length scale that is present in this problem is A naught by A. This is the only length scale in the problem. Apart from that, I do not have any other length scale. So I take A or A naught divided by mu g and take a square root of that. So length divided by acceleration is going to be t square, and square root of that will be t. So this is my damping time scale, and that is my oscillation time scale. So these are the two time scales that are present in this problem. Given these two time scales, now I can go ahead and estimate what is d by dt. So using this, we want to estimate what is 1 by E d by dt, under the assumption that small damping or friction. That's the problem statement. We have over here assuming small friction, so the damping is happening at a very slow rate. Estimate the rate at which energy in the oscillator is changing and the rate at which amplitude is changing. Alright, so we will start with the expression dE by dt, 1 over e d by dt, because it's simple in the sense that it contains only the dimension of time. So by using naive dimensional analysis, if there was no damping, energy will be constant, but because of damping, energy is changing. Naive dimensional analysis tells us, like we did in the last example of LCR circuit, we use naive dimensional analysis. It says 1 over e d by dt is simply of the order of 1 over t damping, which gives me the result that 1 over e dE by dt is of the order of square root a naught by mu g. Well, let's take a to be instantaneous amplitude, and if I take a to be instantaneous amplitude, I can drop this a naught from here. Let's just simply take a as instantaneous amplitude at that point. So as instantaneous amplitude changes, damping time also changes, and we'll take this a to be that instantaneous amplitude. So we'll assume over here that a is instantaneous amplitude. So this gives me that 1 over e d by dt is proportional to square root a. Let's take another approach. So this was approach number 1. Let's take another approach where we'll use some physical input using physics of damping. Physics of damping. 1 over e dE by dt can be written as 1 over e delta E over delta t, and this I can write as 1 over e, I can write as 1/2 Ka square, because a is the instantaneous amplitude and spring constant is k. Actually spring constant is effectively 2k, so 1 over 2Ka square times delta E. Delta E is the loss of energy, which is equal to the work done by the friction, and friction force is mu mg. Work done by it is 4 times, because the friction force drags over one cycle of oscillation, drags the mass by 4 times the a is the instantaneous amplitude. Therefore that's the work done by the friction force divided by time period of oscillation, because we are talking about one full oscillation. The amount of energy lost in one oscillation divided by one oscillation time period, that is delta E by delta t. This is a good approximation when damping is very slow. So when we simplify this, we get 1 by 1 Ka square times mu mg times 4a by t oscillation, and t oscillation is 2 pi square root m by 2k. The important real result here is that everything here is a constant apart from the fact a, which is the instantaneous amplitude. We find that this result gives me something that is proportional to 1 by a, in contrast to the result from previous where I got it proportional to 1 by e square root dE by dt. So the summary is that naive dimensional analysis gives me 1 over e dE by dt proportional to square root a, while physics of damping gives me 1 over e dE by dt proportional to 1 over a. Now only one of these things could be correct, not both of them cannot be correct. How do we find out which one of them is correct? Remember, in the case of the LCR circuit, we got both the results to be identical. In both the cases we got the same expression. There the naive dimensional analysis and physics of damping give me equivalent result, but in this case we don't find that to be true. So what's going on here? Whether either the naive dimensional analysis is correct or it is the physics of damping which is correct. How do we find that out? For that, we can only know if we solve this equation, find out the energy, and solve the equation of motion, which is over here. Solve this equation of motion, find out the solution of this, and find out at what rate energy is changing, and compare whether it's changing with instantaneous amplitude, square root of instantaneous amplitude, or 1 over square root of a. Here's one easy way of doing this. Rather than talking about energy, we can also take we can start out, we can calculate 1 over ed by dt in terms of instantaneous energy. Instantaneous energy in the oscillator is 1/2 Ka square, assuming the damping is small. So over the one time cycle there's not a lot of energy that is lost, so I can assume that the energy is roughly constant over one oscillation, and it's 1/2 Ka square. Then d by dt is d by dt of this, which is Ka dA by dt, and if on both sides we divide by 1 over e, we get Ka by Ka square, which is the actually there was no half here, the energy is Ka square, spring constant is effectively 2K, d by dt is d by dt of Ka square, and there should be a 2 here, and therefore all the 2 is not important, but let's keep track of that. So we get 2 Ka over here, energy is Ka square, we divide that times dA by dt, and this becomes I get bunch of cancellations, I get K and A to cancel, and I'm left with, at the end of the day, 2 by A. 2 by A dA by dt. So what do I get from here? I get from here that 1 over E d by dt is nothing but 2 by A dA by dt. This is 2 by A dA by dt, and from here I conclude that dA by dt is equal to A to the power 3 by 2, not equal to but proportional to that. Oh, this should have been there's a mistake here. This should have been the inverse, so let me correct that. This should have been mu g by A, and therefore over here I get one by square root A, and therefore I get here e to the power 1 by 2. And coming to this one, this gives me A cancels out, and I get dA by dt is proportional to a constant. So it doesn't depend on A. dA by dt doesn't depend on A. So in one case, naive dimensional analysis says that dA by dt is changing as square root of A. Well, actually it should be minus, because we know that amplitude has to decrease as with damping, and this is a negative constant, and dA by dt is proportional to a negative constant. So this says that the amplitude is decreasing at a constant rate, and this says that the amplitude is decreasing as a square root of A. So let's find out which is the case, and for that what we'll do is we'll solve this system numerically using NDSolve. So let's take our equation to be, let's get rid of all the dimensions, mg, etc. So this is our equation of motion was mx double dot equal to minus 2kx minus mu mg sin x. If I substitute m equal to 1, 2k equal to 1, mu mg equal to 1, etc., or mu mg equal to 1 with a small coefficient as minus 0.2 or something, like over here. This is identical to that equation, except that we have removed the dimensions from the problem. And this is the equation we want to solve. This is something that we cannot solve analytically. What we have assumed here is that the damping term is small, so that the coefficient we have taken is 0.02. You can go ahead and play around with this coefficient, but this is how we do. We use NDSolve to solve this equation. We set up the equation. The set of equation that we are using is z double prime of t is minus zt minus 0.02 sine of z prime of t. So this is my equation. We're simply implementing NDSolve. This is my differential equation. The boundary condition is z0 is 1 and z prime of 0 is 0. With these boundary conditions, I want to solve for z of t from 0 to 100, some large value of time. And when I execute this, again I get a solution in form of this replacement rule. From this I have to extract this interpolating function. That's what I've done here by saying zt slash dot NumSolve, so substitute zt for NumSolve and plot it from t from 0 to 100, and we get this beautiful plot over here which shows that the amplitude of oscillation is actually going down linearly. It's a very clear case of showing that when damping is small, the oscillation amplitude is simply decreasing linearly for the constant friction force case. Therefore, what we learn from here is that the physics of damping gives me more accurate result, while naive dimensional analysis gets me an incorrect result. So this is physics of damping is right and naive dimensional analysis is wrong. So what we learn from here is naive dimensional analysis is not going to always give us the correct result. Most of the time naive dimensional analysis works very well. It gives me a good idea of what's happening in the problem, but not always. And this is an example where we find that happens to be true. We have to cross check the naive dimensional analysis with physical input, and we should trust naive dimensional analysis only when we can correlate or cross check with some physical input. So therefore, when you use dimensional analysis, you have to be a little bit careful, and oftentimes there's always useful to cross check it with some known result or something that you can validate across. And in this case, when we validate, we find that the naive dimensional analysis gives us the wrong result, and it is the physics input of damping that we use gives us the correct prediction for the rate at which amplitude is going to change. So this is all for today, and we'll see you in the next video.